Okay, hi everyone. So we're going to try this video thing. There's three main things I want to do in this video, and they all work together in a straight line and kind of work in sort of increasing levels of complexity as we go. So the first one is to do the electric field outside a charged conducting sphere, which we did in class, but will be a good refresher on Gauss's law and the symmetry arguments that are part of Gauss's law, or at least the way we use Gauss's law. And then the second will be to get the potential function near a charged conducting sphere, which again, we've done in class, but will be a good refresher. And then the third will be a new problem where we'll take two charged conducting spheres, hook them up with a wire, and kind of see what that does to the charge distributions on each sphere. It's kind of an interesting problem. But the first two are kind of components of the third one. And I'll explain how as we get there. So let's start with the first one. So in this first part, we want to figure out the electric field outside a charged conducting sphere. So let me draw that. So um, here's number one. Oops, number one. E field outside a charged conducting sphere. So let me draw that sphere. So here's what a sphere looks like. Kind of looks like this. That's not too bad. Let's give it a radius. Call the radius of the sphere big R. And there's a few things we can say for sure about this sphere. So it's charged. Let's give it some total charge Q here. Maybe a big Q. And we know where that charge lives in equilibrium. So in equilibrium, we talked about this a lot in class, but we argued that the charge had to be distributed on the surface. And maybe the best or the cleanest argument for why that is using Gauss's law. So if I imagine drawing a Gaussian surface that's inside this sphere. So I'll take another sphere that's centered at the center of our actual sphere of charge. So that red sphere that I just drew in there is a Gaussian surface that's spherical, that's centered at the center of the sphere. And if I apply Gauss's law here, which says that if I take an integral over that surface of E dot dA, that has to be equal to the charge enclosed by the surface over epsilon naught. But we also know for sure that in equilibrium, the electric field inside has to be zero. We know that for sure. E inside has to be zero, because if it wasn't, then the sphere wouldn't be in equilibrium. If there was some electric field inside the sphere, then charges would continue to move until they found some orientation where the electric field was zero. So they'll just keep moving until electric field is zero. And then once they stop moving, it's in equilibrium, electric field inside is zero. And that implies that if I do this integral, 0 dot dA equals zero. And according to Gauss's law, that's equal to the charge enclosed over epsilon naught. So that means that the charge enclosed by my Gaussian surface has to be zero. And that means that all of the charge has to be on the surface of this sphere. That's because I can make the radius of my Gaussian surface as large as I want, as long as it's not larger than big R. I can make the exact same arguments I made in any of these steps here. All those arguments still work until I get outside of the sphere, which means that there can be no charge enclosed anywhere inside the sphere, so all the charge has to be on the surface. So that's the first argument. So that's kind of cool, kind of a nifty argument. And now for the electric field outside. So let me take another Gaussian surface. I'll make this one green, and I'll make my Gaussian surface here another sphere centered at the same place as our actual sphere of charge. But I'll give it some radius that's larger than big R. So little r bigger than big R here. So I guess red was inside the sphere. And green will be for outside the sphere. So I guess I'll do that here. So outside the sphere. And the question that we're trying to answer is, what's the electric field outside the sphere? So because of the symmetry, we can use Gauss's law, which is kind of nice. So let's do that. So the electric field dot dA integrated over the entire Gaussian surface has to be equal to the charge enclosed over epsilon naught. We know this time that the charge we're enclosing is big Q, the total charge of the sphere. All of the charge on the sphere is inside of our Gaussian surface, so that's just big Q. The way we evaluate the integral expression is we make these symmetry arguments that we've been making in class. So the reason why we chose our Gaussian surface to be a sphere is because we know that if we do that, then dA, which is the sort of the normal vector to the surface at any point, for every little infinitesimal piece of area, will always point radially outward from the surface of the sphere, which is useful to us because based on the symmetry of our actual sphere of charge, we know that the electric field also has to point radially outwards. It wouldn't make sense for it to not point radially outwards here. It has to point away from that sphere, away from the center of the sphere. What that means is that E and dA are always parallel to each other. So if we do E dot dA, we can just write that as E dA, because cosine of the angle between E and dA is 1. So that's nice. But the other symmetry argument we can make is that if we have a spherically symmetric collection of charge, then the only thing that can affect the electric field is how far away from the center of that distribution of charge we are. The electric field cannot depend on where on this green sphere you are because the charge distribution is symmetric. So I can rotate the charge distribution as much as I want, but it shouldn't change the electric field anywhere on that green surface. That means the electric field's constant everywhere on the surface. So I can then pull the electric field out of this integral, because even though the electric field isn't constant as you move closer to or farther away from the sphere, it is constant everywhere on that sphere, on the green sphere, the Gaussian surface. So then I'm doing E integral dA. Integral dA is just the surface area of the sphere. So that's equal to E times 4 pi little r squared. And by Gauss's law, that's equal to the charge enclosed, big Q, over epsilon naught, which means that the electric field, or the magnitude of the electric field, is equal to Q over 4 pi epsilon naught r squared. Or if you want, based on the definition of epsilon naught and K, that's the same thing as KQ over r squared. That's a really cool result because it suggests that the electric field outside of this spherical conducting sphere is the same as a point charge centered at the center of our conducting sphere. So you get outside of this sphere and it looks like a point charge, at least in terms of the electric field, which is a really cool result if you think about it. Okay, so let's use that result now. So part 2 now is to find the potential near a charged conducting sphere. So part 2 here, let's scroll down. I'll leave this electric field result at the top. So 2, potential near a charged conducting sphere. Okay. So let me redraw our sphere. So our sphere looks like this still. It's the same sphere, let's say. So it has some radius, big R, and it has some total charge Q. And now I want to know what's the potential at some point nearby. So if I pick some point in space out here, call it point P, then what's the potential at point P? V equals what at that point? That's the question we want to know the answer to. The way that we calculate potential differences is through our definition of potential difference, which is you take this negative integral of the electric field along some path, so path integral from some starting point A to some ending point B. You move along some path in some electric field and you get a potential difference. So very similar to a potential energy integral, but again, the interpretation of the potential rather than the potential energy is the potential is sort of the potential to have a change in potential energy. There's no actual charge moving through that electric field. It's just evaluating the effect of our spherical charge by itself without it actually interacting with anything else. We did this problem in class, and I just want to run through it again in some of the arguments. The first step that we have to make in order to write down a potential function is to decide where the zero of that potential function is. It's convenient to define infinity as zero for this sort of charge distribution. So let's do that. So the potential at some point P, which I'll say is a distance little r from the center of the sphere, is equal to, or R naught, I should say, is I'm integrating from infinity. So the lower bound of the integral will always be infinity. We're really taking a potential difference from infinity to R naught of the electric field created by our charge distribution along some path to get in. So in principle, I would really need to know what the path I'm moving along is. But in practice, I can always write the electric field this way. Electric field is always kq over r squared r hat. And we showed that in part 1, where it kind of looks like a point charge, except it's really a conducting sphere with all of the charge on the surface, but the electric field looks the same. dl will be a little bit of path, but if we do this in polar coordinates, we can always write dl as some infinitesimal change in r, in the r hat direction, plus some infinitesimal arc length in the theta hat direction, where theta hat means that you're moving sort of this way, like around the sphere, and r hat means you're moving sort of this way, radially inwards or outwards from the sphere. We can always write dl that way in polar coordinates. That means that if we do E dot dl, we only get the r hat parts, because r hat dot r hat is 1, and r hat dot theta hat is 0. If I write that all out like this, E dot dl, then I get kq over r squared r hat dotted with dr r hat plus r d theta theta hat. And the dot product r hat dot r hat gets 1, r hat dot theta hat gets 0, because they're always perpendicular. And so this is equal to kq over r squared dr, which means that my potential integral then becomes the negative of the integral from infinity to r naught kq over r squared dr. All right, scrolling down. Then to move over here to the other side, then the potential, if I evaluate that integral, I get KQ over R. The minus sign cancels with the R to the minus 1 that would come down when you take a derivative of this, evaluated at infinity and R naught. So that gets KQ over R naught, that's the upper bound, minus the lower bound, KQ over infinity. So that second term goes to 0, and the potential at some point P, a distance R naught from the center, is KQ over R naught. Again, that's kind of a nice result. There's sort of an interesting result here too that we can think about, like what's the potential of the sphere itself? That would mean that, what potential is this sphere at? If we talk about the potential of something, sometimes we say, what's the voltage of it, right? So what's the voltage of this battery? Or we talked about what's the voltage of the Van de Graaff generator. We argued, or I claimed that the voltage of the Van de Graaff generator was somewhere in the 100 to 200,000 volts range. But when we're talking about the voltage, we're really just talking about the potential difference from 0. So for us here, we can ask, what's the potential of our conducting sphere? So I'll write that. What's the potential or the voltage of the conducting sphere? Well, at this point, it's kind of easy to answer that because I know that the potential for a distance R naught away is just KQ over R naught. So the potential at the surface is equal to KQ over R. And maybe, and that's fine. I know actually, in fact, this is the potential anywhere on the sphere, not just at the surface, inside too, because there's no electric field inside the sphere. So if I start integrating the electric field along some path inside the sphere, I get nothing, because if I integrate 0 along any path, I get no change in potential. So the potential anywhere in the sphere is KQ over R. So this thing is potential everywhere it's on the surface and interior of the conducting sphere. That's kind of nice. And I'm going to stop us here, and then I'll do the third part in a separate video.